So the second part of section 3.3 is taking a look again at how derivatives shape graphs. So let's now look at two graphs. We've just talked about increasing and decreasing. I want you to look at these two graphs and notice what things do they have that in common? What are in common about them? What do they share? So notice that in both cases, we have that f of 0 equals 0. We have that f of 1 equals 1. We also have the fact that both of these are increasing. In both of them, their derivative is greater than 0. But yet by looking at them, we can see that they do have a difference to them. We have one that's shaped like this, and we have one that's shaped like this. So this difference is the next step in the derivatives. So the way that we define this next idea is the idea of concave up and concave down. And we can determine when a function is concave up or concave down on an interval if the function lies above the tangent lines for concave up, and if the function lies below its tangents on the interval for concave down. So what that means is, if you were taking a look, for example, at this function that you see here, just this basic graph, if I were to think about the values for which I have 0, so I'm doing the best I can here, but it's not perfect, but that was the idea, something like this. Okay, this is where our function, our derivative, is going to be 0 because we have the horizontal tangents. So we want to think about that. And then what I want you to see is we can see pretty easily about the first derivative. We can see that on this function, we are decreasing, then we are increasing, we are still increasing here, and then after here, we are decreasing again. So that tells us something about the derivatives. So I want you to notice that we basically have the 4 different pieces here. So when we think of the second derivative, the idea is the second derivative is going to be positive when the function is concave up, and that's when f lies above its tangents. So if you notice, for the first piece here, if I was to draw a tangent line, it's going to look like this, and that tangent line is going to be under the function. That's what it means to say that the function lies above its tangents. That makes sense. So in this case, we actually have a positive second derivative. If I'm here, notice again, if I was to try to draw a tangent line, I would draw it there. And in that case, the function again is going to be above its tangents. So again, I'm going to have this positive on the second derivative. But over here, notice a tangent line would look like this. Now I have that f is below its tangent, so I'm going to be concave down. What that means is a negative second derivative. And at the end here, same idea. If I do this, notice that my function is below its tangent line, and so I'm going to have this as well. So this is the idea that concave up is indicated by a second derivative that is greater than 0, and concave down is indicated by a second derivative that is less than 0. And actually, I'm just going to write that back down on the bottom here. So the concavity test is the graph of a function is concave up if the second derivative is positive, and concave down when the second derivative is negative. So notice we'll often say up like a cup, and we'll say down like a frown. So these are the 2 pieces of concave up, here and here. And these are the 2 pieces of concave down, here and here. And we'll look at some examples and see what else we can see. So here we have a function. We want to know when is it concave up and concave down. If you're asked about that, you got to the first thing you should think is take that second derivative. So if you want, please take a moment, take that second derivative. First, you got to take the first derivative and then take the second derivative and see what you get. And then, pause and come back. So because this is a polynomial, our second derivative ends up just being linear here since it started as a cubic function. So in order to find any values where the concavity might change, because that's what's important, just like something changing from increasing to decreasing, we want to look at what values make the first derivative 0. To find out about concavity and where it might change its concavity from concave up to concave down, we want to set the second derivative equal to 0. So when we do that, you can see that we get x equals 2. And then a good idea is to, of course, to determine what's happening, is to take a look at a number line with the second derivative. So I'm just going to put values into my second derivative. Am I getting something positive? Am I getting something negative? That's going to tell me about concave up, concave down. So if I put something into the second derivative that is less than 2, like 1, right into here, you can see that 6 minus 12 is a negative 6. So I'm going to have a negative. But if I were to put in something greater than 2, like 5, I'm going to have 30 minus 12, and that's going to be positive. I don't care the value, I just care positive or negative. So this tells me that for this function that we have right here, it is going to be that the second derivative is positive if x is greater than 2, which is what we got from our number line. So f is going to be concave up on the interval 2 to infinity. We can also see from our number line that the second derivative is negative. The second derivative is less than 0 when x is less than 2. So we're going to have concave down on the interval negative infinity to 2. Okay, notice there should be a little space there. Okay, so just a couple definitions, theorems, and stuff about this second derivative idea. So what this is called, so a place where the concavity might change. So for example, you might be concave down and then you become concave up. Maybe it's better to do something like this. You'll see pictures, but concave down to concave up, maybe something like this. So there's this point here where it changes, and that point is called an inflection point. So let me write that in. Just need to find my pen. There we go. Inflection point. If the concavity switches, so positive to negative or negative to positive. And this happens at the extreme points of the derivative because, of course, it is when the second derivative is equal to 0. And so that's like the idea of the extrema of the first derivative. So really you can just think it is the second derivative that you're setting to 0. So a theorem we have is if we have a function that is continuous and differentiable on some interval, if there is an inflection point on that interval at some value, then either the second derivative is 0 at that point, or the second derivative does not exist at that point. Okay, and then a last note that if the second derivative equals 0, that doesn't imply that there has to be an inflection point. You still have to check and see if the concavity changes from, say, down, concave down to concave up, or you could even have, I'm not sure if I can do it, concave up to concave down. You could have something like that. You could have concave down like this. You could have concave up like this. So those are all the things it can do. Okay, let's take a look at a couple examples here to finish up this section. And obviously, this all combines to make graphing a function even more specific. So here we have x to the fourth. A lot of you may be like, well, I know what a parabola looks like, so I'm pretty sure I know what x to the fourth looks like. The question, does this function have any inflection points? Take your first derivative and take your second derivative, see what you get. pretty basic second derivative here. If we set it equal to 0 and do a ton of work, we really just get that x equals 0 is the only place where the second derivative is equal to 0. So we have x, we have our derivative, we have our second derivative, something like that. And then the only thing we got was 0. We can see pretty easily that our first derivative is going to change. So if you put values into our first derivative that are less than 0, you're going to be cubing them. So that's going to be negative, and so that's going to tell you that you're decreasing. If you put in positive values into the first derivative, you're going to get values that are positive. So that tells you that the function is increasing. When you put values into the second derivative, you can see that no matter what you do, you're going to get positive numbers because it's 12x squared. So that tells you that you are positive and positive, which just tells you that you are concave up. So you're concave up like a cup. But notice that you're decreasing concave up because on the left side of 0, decreasing but concave up. And then after 0, you're increasing and you're concave up. Function is increasing, but you've got that concavity of concave up. And so not surprisingly, x to the fourth really just looks a whole lot like x squared. It just has a flatter, and it's not completely flat, but it has a flatter, of course you should have symmetry, look to it down at the bottom. So it looks a lot like x squared, but just a bit flatter because those fractions are being raised to the fourth power, which make them very small, which create a very function that's very close to 0 when you are close to x equals 0. So what we find is that this has no points of inflection, because there's no place where the concavity changes. The concavity is up the whole time, concave up. All right, let's see about this one. So does this function have any inflection points? So if you want, pause, take a moment, and find the first and second derivatives. I'm going to rewrite it. That helps me with my first and second derivatives. Okay. Key thing here, you do not need the quotient rule. So a lot of students, or at least I have seen it in the past, but you should realize that when you take a function f of x, like you see there, and you have 3 over x, because the numerator is 3 and the derivative of the numerator is then 0, this is not a rational function that needs the quotient rule. You don't have any variables in the numerator. So I'm just going to rewrite it and take my 2 derivatives that way. Bada bing, very fast. Okay, now I'm going to do the same thing I just did before. So the thing that we have to think about here is you do have to test that there is a value that makes the denominator undefined. So although there's nothing that makes the numerator 0, there is a value that makes the denominator 0. So x cannot be 0. That's an issue for us. So it is something to check because of what definitions and theorems we have. We want to check on either side of 0 and see what is happening. So by putting values into the first derivative, notice if you want, you're going to have negative 3 over x squared if I rewrite it. So any negative value that goes into that first derivative is going to come out positive in the denominator, and any positive value that goes in the denominator is going to come out positive. So you can see that this is going to be always negative, this f prime. So it's telling us that our function is always decreasing. So decreasing on either side of this 0. And then our second derivative, notice if I put in a negative value, something less than x being 0, I'm going to have a negative here. And then on the other side, I'm going to have a positive. So this function is always decreasing, but on one side it's concave down, and on the other side it's concave up. So that helps with the shape. Something that we should know just about a function like this is that it has a vertical asymptote at x equals 0, and that's why we're getting that issue at 0 for the first derivative, and the second derivative we can't put in 0. So that's something to just remember, is that we have that vertical asymptote. So this is just a sketch, but we can see that if we put in very large values of x, our y is going to be very small. If we put in very large negative values of x, our y is going to be very small, but negative. And so we're also know that we can't approach a vertical asymptote. Like we can't touch it, right? We can only approach it infinitely close. This is just a sketch, but you can see that if we have x being 1, we do get 3. And if we have x being -1, we get -3. So not surprising, this function does something like this and just heads down. But notice that's concave up. It is concave up. The tangent lines to this would be underneath, so the function would be above. And over here, again, you want to remember we're going to get close to those two asymptotes, the vertical and the horizontal. So we have something that looks like this. Notice that that's concave down. If we were to draw tangent lines, the function would be below those tangents. And that's that function. And then the last thing for this section is the second derivative test. So basically the second derivative test can tell you something about the first derivative if you want. It's just another way to think about relative mins and relative maxes using the second derivative, which sometimes is helpful. So let's say that we have a function whose derivative at a value is 0, and let's say that that derivative exists at and near x equals c. So we have all that information, which is just telling us that there's things we can do. If the second derivative is greater than 0 at that value of c, then there is a relative min at x equals c. So remember, the key thing here is that the derivative is already 0 at that point. The second derivative just tells us that it is a min or a max. If it is less than 0, then there's a relative max. And if there is the case that it is equal to 0, the second derivative at that point, then unfortunately this doesn't tell us anything. It gives no info. So what that means is, if the second derivative is positive, you want to remember that that's concave up. So this is what's happening. So it's not surprising that there's a relative min there. But when the second derivative is less than 0, remember that means you're concave down. So you have a situation like this. So it's not surprising that you actually have a relative max at the value that you care about. Because remember, the derivative at that value is already 0. That's given to us. So that's creating situations like this or this, so that you have those mins or maxes. Okay, so the last problem here is just what are the relative extrema? That's the local relative min max, but we're going to use the second derivative test. Notice we've already done this problem. Earlier today, we found a first derivative, and that first derivative was 2 times x minus 1 times 2x plus 3 times x minus 2. However, what we need to do is multiply this out. So I'm just going to tell you what it is multiplied out. Point is, we need the second derivative. So this one multiplied out is 4x cubed minus 6x squared minus 10x plus 12. So if you want, you can pause and take the second derivative. That's what we need, second derivative. Now we don't need to do anything with this. All we need to do is plug our critical values that we already got using the first derivative test, finding the critical values, and then just plug them in. So we're going to take our critical values. We already know what they are from the first derivative. We've done that. Remember, that was -3/2, 1, and 2. So just go back in your notes if you want to find those values again. What this tells us is that we can find out relative min or relative max simply by plugging these values into the second derivative. So all we do is plug it in and see whether we have a value that's positive or negative. So we're plugging things into the second derivative. You can see that if we plug in -3/2, and you do the work for that, if you want, you can pause, you should get 35. And that is positive. That's greater than 0. So what the second derivative of test tells us is that at -3/2, our function is concave up. So if it's concave up, we have a relative min. And we already know what it is because we actually already found it with using the first derivative test. But it's a relative min of, and then that was that -23.4375 at x equals -3/2. Again, we already knew this. If we plug in 1, you can see the second derivative, we get 12 minus 12 minus 10, so we get negative 10. More importantly, that is less than 0. And so what that tells us is that our function is concave down at x equals 1. And so that's going to create a relative max. So relative max, so you can see how the second derivative test could be handy. Relative max of, and we end up with, remembering from before, that's 0 at x equal 1. So again, I'm not finding these values, I'm just using them from our previous notes. And then when we put in 2, if you put 2 into the second derivative, work it out, you should get 14, which is greater than 0. So again, we are dealing with something that is concave up. So we have a relative min of, and remember the y value is -2, relative min of -2 at x equals 2. So the second derivative test, again, just a way to find out your relative extrema. So if it's a lot of work to create, these sign charts and things, you might want to use the second derivative test to test for relative mins and maxes, especially if the second derivative is pretty smooth, pretty nice. So this is that graph that we've been looking at a couple times in this section, and it's in Desmos. So I just want you to see here that from what we've been doing, we have our value at the bottom. So we have our value at -3/2. Notice that we have a relative min here. So you can see those values that we found before. We have a value up here. We have that 1, 0. And we also have the 2, -2. So notice that from all the work we did, the function is decreasing down to that -3/2. Then it's increasing after that, and increases all the way to 1, 0. Then it decreases down to 2. Then it increases back to 1. Notice as well, however, that there's a couple other points that would be important on here. And so if we had taken that second derivative, which we didn't, but if we had, and we had found out when it was equal to 0, we would have found where we had some points of inflection. So what I want you to notice is that this function is concave up, concave up, concave up, concave up, all the way until somewhere around here. I don't have the values because we didn't solve it for the second derivative for 0, but there's some place right around here, where notice that it changes from concave up, like a cup, to then the concave down. So notice somewhere around here. So if you found the points of inflection, it would be here. You should also find another point of inflection somewhere around here. So notice again, there it's going from concave down, and then after that value, it's going from concave up. So it doesn't look like they're probably pretty nice values, not for sure. I just haven't done the work on that to find out what they are. But they're somewhere here, and then somewhere here. So there'd be 2 points of inflection that you'd find, and you'd notice that the concavity changes on either side. And that's that function we've been working with, so it's kind of cool to see it with all the pieces that we've been talking about. That's section 3.3.